All right, for the last topic here in our additional aspects to aqueous equilibria, we get into solubility equilibrium. So going back to you guys knowing what salts are insoluble, what salts are soluble, this is kind of going to border on that talk right here. But what we're going to deal with here is mainly the salts that up until now I would always say are not soluble. You put them in water, nothing dissolves. And it turns out that nothing is technically insoluble. Everything at least dissolves a little bit. But what we've called insoluble up to this point is just something that it is soluble, but it's not perceivable by the naked eye. You would have to have some type of ion detector in order to know that these things are dissolving. And the way we express this is another equilibrium constant. Once again, the way we write equilibrium constants never changes. Products over reactants raised to the power of their coefficients. But this final equilibrium constant that we're going to talk about for this course is another, obviously, equilibrium constant based off of concentration. So what that is what we call the solubility product constant, or KSP, SP standing for solubility product. So if we look at this here, I've got an example of the KSP equation for silver chloride. So what you're going to do is you're going to write a salt dissolving. Up until now, we'd say silver chloride is the halide salt of silver, which is going to be insoluble. And you're going to call it insoluble on your AP exam. But it is important for you to know that it is, in fact, slightly soluble. It just does not ionize completely. So I want you to pay special attention to our states of matter here, because once again, we see a solid, and solids do not get written in an equilibrium expression. So this is very important. A KSP is never going to have a fraction. It's always just going to be basically the product side of a reaction, which turns into the numerator. So you just get one single line here for our KSP expression. Now, obviously, if we had more of these dissolved, we'd end up with squared or cubed or whatever the case might be. But we are writing KSPs here. KSP expressions are just a single line, as we have right here. Now, these are going to be incredibly small. In fact, KSPs are going to be smaller than even a lot of the acids and bases, the Ka and Kbs that we've seen. It is not something that's going to be even close to the -4s or the -3s. You can find this on page 1063 of your book in table D.3, and what you'll get is a bunch of different KSP values for salts. So something that we're going to have to do with these is write an ice table. So what you can get here is, here again, we've used the silver chloride as an example. We do not care about our salt here, but this is very important over here. Once again, because we have no coefficients, we just get a value of x here in this ice table. Now what you're going to do is then place that into the KSP expression. And since the KSP expression for this one was just the silver ion times the chloride ion, it becomes x times x, or x squared. So what we can do with that then is find what we call the molar solubility. This is going to be one of the first few questions on any AP KSP problem. Is they're going to ask you for the molar solubility of a salt. So what we do is we take the result of our ice table, which we see right here, and we are going to set the KSP, in this case of silver chloride, equal to the results of our ice table. So this KSP would have to be given to you, or you'd have a table such as your book in order to find that. And if we set that equal to the result of our ice table right here, what we get is the molar solubility. And anytime you're asked this on the AP exam, they're just asking you for the molarity. So when they want the molar solubility of a salt, they want you to solve for the value of x. And in fact, most times they're going to ask for a specific ion. What's the molar solubility of the silver ion? Or what's the molar solubility of the chloride ion? So since both of those are represented by x, the molarity of these ions in any saturated solution of silver chloride, whether it be a liter, whether it be half a liter, whether it be 100 liters, once you let this come to equilibrium, the solubility, or I should say the molarity of these salts, would be this. in the case of silver chloride. This is what we also call the saturation point, meaning once we reach that molarity, the solution is said to be saturated and no more silver chloride will dissolve in water. Now, where this gets tricky is when we have more than two ions formed. So if we take lanthanum 3 chloride here, take a look at what happens to this ice table. All of a sudden we get 3x in this particular portion of the ice table here. So when we carry that into the equilibrium expression, which is that right there, so notice that we have cubed this because I want to show you the dissociation of this here. Okay, this would be 3 plus 3 chloride. So that's why we've got this cubed right here. So you probably want to do that. I should have shown you that there. You always want to write the dissociation equation of these salts here. But that cubed right there, notice what this does now that we get the 3x. We still get 3x here, and what people never want to do is they think it's wrong that that 3 shows up twice. Yes, that 3 essentially comes from the same place, but it's so important that you do not forget to both cube this as well as place 3x cubed in there. So what I'm going to do is I'm going to cube this expression into 27x cubed. And this time, instead of getting x squared, look what happens just because we have 3 of these things dissolve, 27x cubed. So now when it goes to finding the molar solubility of this, we've got a little bit more algebra to do. We're going to set the KSP equal to our term here, and then notice now what our molar solubility is. Now, if they happen to ever ask for the solubility of the salt in general, they're asking for the value of x. So if they want the solubility of the salt itself, they're asking for the value of x. So if in this case they ask for the solubility of the chloride ion, we have to go back here and check what the value of the chloride ion is. That is 3x. So what we'll do is we'll multiply then the value of x times 3 to find the solubility of the lanthanum, or I'm sorry, the chloride ion. Okay. I'll go ahead and leave this here, and I'll show that you guys can pause this if you want to try this on your own here, but I'm not going to talk about this. So if you want to pause this to go ahead and work on this problem, that's fine. You've got the solution right there. Another thing that we are going to have to keep in mind is the common ion effect. How will that value of x change if we have other ions in solution? So what we've been doing until now is simply pure water calculations, but is that solubility, is the value of x going to be affected should we place a salt in a solution that contains a common ion already? So here we have copper 2 hydroxide. This is going to be a 3-part problem. One, I want the molar solubility of copper 2 hydroxide in pure water, so what we have been doing. But then I also want it in copper 2 nitrate, which contains the common ion copper 2. And then also in the sodium hydroxide solution, which contains the common ion here, hydroxide. So the first calculation here is in pure water, and this is what we have been doing. So what you can do there is, again, you can go ahead and find the results of the ice table for that guy, and what that would simply be is if we're working with copper 2 hydroxide, that would dissolve into the copper 2 ion plus 2 hydroxide ions. The results of the ice table will be this, and the KSP expression equals basically our copper concentration times hydroxide squared. We'll put x into there, we'll put 2x into there, so we get x times 4x squared, and that's where the 4x cubed came from up here. So what we have been doing, you'll then use the KSP that I gave you on the previous page to end up and get to our solution of x right there. That's the solubility of copper 2 hydroxide in pure water. Now if we do this in copper 2 nitrate, we need to do an ice table. So what we're doing here is this time when we take our ice table, we'll go back to this. This time we have an initial concentration of copper, which is 0.1 molar. So instead of 0, we have an initial concentration of our copper ion. So at equilibrium, this is going to be 0.1 plus X and then just 2X down here. So that's why we have this constant in this expression up here. Now what we'll do is, just as in all previous ice tables that we want to avoid the quadratic equation, we're going to assume that X is negligible and just get rid of it. So this time when we solve then for the value of X, we're going to see something that is much less soluble than pure water. If we remind ourselves of what the solubility in pure water was, that was 3.419 times 10 to the negative 7th. Okay, so here we get something that turns out to be, well, basically a little less soluble because the presence of a common ion. So this common ion effect is going to shift solubility to the left here a little bit, and we're going to get something that is not quite as soluble as a result. The same thing should happen with the sodium hydroxide. We do have an initial concentration. So what we get here is something that, once again, is much less soluble due to the presence of this common ion. Once again, we had a 0.1 molar solution. We're going to assume that 2X is negligible, and we're just going to end up with this expression right here, solve for X, and we get this value right here. Solubility is going to decrease due to this presence of this common ion. Very important that we always check our work. No matter what, whenever we have a salt dissolving in a common ion solution, the solubility should decrease. Okay. One of the last things, if you get one of these questions, you'll be asked to do is to predict whether or not a precipitate will form, or what the concentration of a solution needs to be in order to precipitate an insoluble salt. So what's going to happen here is we're going to mix two salt solutions, sodium sulfate and calcium chloride, and the salt, hopefully, that we understand we're going to form here is the calcium sulfate salt. So what we want to do first is we want to write the net ionic equation of calcium sulfate, which we get right there. Now afterwards, we want to then determine what our value of Q is. So what we're going to do is we're going to just change KSP into Q, and we're going to write our equilibrium expression, and we're going to input our two initial concentrations of our ions, 0.1 and 0.05. That's where those are coming from right there. And there's our reaction quotient. Now what we know then is we are much, much greater than our KSP. So our KSP is 7.1 times 10 to the negative fifth, and our reaction quotient is 0.005. So since Q is larger than KSP, what this tells us then is this reaction needs to shift to the left. We're going to form a precipitate, and this once again is in your notes as far as the relationships of K and Q go. Now in this case, what this tells you here, if you're ever asked what concentration of an ion would be required to precipitate a known concentration of the ion, you just want to place the known concentration of the ion next to your unknown, plug in your KSP value, and this will tell you that in order to form a precipitate in a 0.1 molar solution of calcium chloride, we need a sulfate ion to have at least this molarity here to precipitate calcium sulfate. If it's any greater, it will still precipitate calcium sulfate, but if it's less than this number, we will not get a precipitate to form. So if you're asked a question that says something to the effect of what is the necessary concentration in order to precipitate the solid, you simply want to put in the concentration of the ion that you know, plug in your KSP and solve it, and what that will tell you is the concentration of the unknown ion in order to precipitate that salt. Once again, I'll leave this up here for you. You can pause this to get your questions written down, and if you want, I can check those for you if you happen to do that. The last bit of this chapter is to alter the solubility of these particular insoluble salts. So ways that we can alter solubility is somehow remove an ion from solution, and that's easiest or most easily done with a hydroxide ion. If you add an acid to this, essentially what will happen is this hydroxide will change into water. So this system will think it's losing hydroxide, and it will shift to the right in order to compensate for that. So most of the times with hydroxide salts, be on the lookout. These are multiple choice questions. Hydroxide salts become more soluble in acid because the acid is changing hydroxide into water. The system thinks it's losing this hydroxide, and it will force it to shift to the right and therefore make it more soluble. Another way to do this is complex ion, and we've done this already. Anytime a complex ion can form, so be on the lookout for metals and ligands. So if you see silver and chloride, if you see ammonium and copper, anything like that that can form a complex ion, that will also increase solubility. So for example, if you see something like that, anytime you see ammonia is kind of something to keep a lookout for, because that's a great ligand in a complex ion.